I got known to this course with Stanford University from Professor Hall. So he recommended us and did some publicity for it. And I read through and I saw also the previous presentations, and it looks really interesting. So I think it was already when I applied or thought about applying, I think it's a very nice challenge also with different disciplines and to work together with people from all over the world, basically. And I knew that it's quite a lot of time also and effort, but I think it's a very good opportunity. So that's why I just said, okay, I tried to apply. I mean, I didn't know even if I have any chance or how many others are applying from ETH. And actually, I still don't really know how many concurrents I had. But I had a really nice interview and talk with Renate Fruchter, our teacher and like the main owner and everything. And it was very interesting to see also her experience, what she told me about this course. I mean, she does it for 28 years now. So it's really quite some long time. And yeah, she didn't really have to say a lot more. She just convinced me, and I'm very happy that she chose me to represent ETH this year. Yeah, and I'm very happy that I did this course. Definitely, yeah, I can only recommend it to other students. Yeah, exactly. And I saw, Conrad, I think you need to enable me to share the screen. And then I can directly go into.
Yeah, I'll let you share. Give me a sec. Okay, you should be ready to go now.
Yeah, perfect. I will also talk a bit more about the requirements and what the goal of the course was during the presentation. So I won't tell you about that now. Okay, don't want to see myself. You can see the screen? I think, yeah. Okay, perfect. Then welcome everybody, and I will present you today the project development and the final project of Team River 2021, participating in the 28th AEC Global Teamwork course from Stanford University. And Team River, that's 7 people from 7 universities, from 5 disciplines and 3 different time zones. And the objective of this course was to do collaborative teamwork, to develop our skills in communication, collaboration, and coordination, and as well to set up our mindset to integrate the design, the model, the schedule, and the costs by building a university building. We were also accompanied by an owner team of 6 owners that were distributed in 4 different countries, and they were mentoring us and advising us during this whole journey. So we met every second week and we showed them our progress and we discussed our ideas. And now I will introduce you to our site, which is located in Weimar, Germany, in the Goethe Park next to the River Ilm. And some site hazards of this site is that Weimar is a UNESCO World Heritage City and it needs to be treated accordingly. Also, we have wind coming from the southwest and tight intersection roads and access roads. But this challenge actually enabled us to really work and focus on a small kit of parts and to have these vehicle restrictions and to integrate them into our design. Also, the hazard of a shallow water table and flood risk was many times discussed, and we found out and investigated several solutions for the different building concepts. So the course is about building, designing, and constructing a 3-story university building for collocated and online courses. And we were given 2 footprints to see on the right, the L shape and the square shape. And also they were given certain requirements for the functional spaces like the area, the orientation, or the room height. We were also not allowed to build more than 9.1 meter above ground level. And we set our budget to 12 million euro, and it was also restricted to have the construction completed by end of September 2025. Furthermore, there were 3 interesting challenges from the industry partners. So first of all, we had the parametric adaptability challenge from Buro Happold, then the sustainability equity challenge from AR Green Consulting, and the buildings as a product from DPR. And with all these requirements, we started into the concept development phase in the winter quarter, where we were working on 4 different alternative solutions, and in the end evaluated them in a decision matrix approach. And during the project development phase in the spring quarter, we then focused on this winning concept and elaborated the details and some improvements. We also created further team targets for our team. They were steering our design from the very beginning, and we divided them into the categories design, user experience, and construction and use. And now I'm going to introduce you to our first stabilized concept called symbiosis. So symbiosis is any relationship or interaction between two dissimilar organisms. And there are three subcategories, which are mutualism, where both organisms benefits, commensalism, where one benefits and the other is unaffected, and parasitism, where one benefits and the other is harmed. And symbiosis was one of our main gestures integrated into our building. So we started with our first concept, which had a quite long cantilever, and this was because we wanted to fit all the room requirements. But there came also the idea to twist and expand the building, where you see on the second concepts. But after some mainly structural mentoring, we really found out that this structural system is very demanding and it limits the architecture. Furthermore, we decided to need to include some of these inclined columns, but they are again taking space away. So we had to step back and do some more brainstorming and interdisciplinary coordination. And that led us to the decision that we can either expand our building or twist it. And also there came the idea to have this stepped basement you see on the bottom right picture. And with this, we gained more space below the ground, and also it solved the problem of this shallow water table. And this led us then to this proposed concept, symbiosis growth and symbiosis mesh. Our architect had the overall vision of the strive for mutualism, accept commensalism, and avoid parasitism. The structural engineers were on one side focusing on sustainable materials like glulam and CLT. And on the other hand, we were working with steel and 3D printed smart slabs for integrating the MEP ducts and the connection to the columns. Our MEP engineer was firstly focusing on building orientation and also on the relocation of some trees in the park. And then we decided for a primary system to use the electric boiler for the growth and the ground source heat pump for the mesh. And this was complemented with secondary systems like the displacement ventilation and the radiant floors. And for both concepts, our CMs decided to use sustainable small-medium enterprises. The material for the growth was provided by just-in-time delivery, and for the mesh, we had an offset storage, which led us to focus on the supermarket approach. We also had a lifecycle financial manager in our team, and he focused on the risk management, sustainable target value design, and also he was calculating the final lifecycle costs. And this leads us to our second stabilized concept next year spring. So as I said, our building is located in the Goethe Park, and so we were inspired by its founder, Johann Wolfgang von Goethe, you see on the right. He's a Renaissance man, a landscape planner, and he was also mayor of Weimar, and he was a poet. So one of his poems is Next Year Spring, referring to something new. And his verse inspired us a lot for our design and also led to our concept goals, which are bridging the gap between the past and the future. And we connect to the past by passive measures, for example, building with round earth, and we reach for the future by active measures and a sustainable process. Again, for this concept, we had, for the first and second concepts, very long cantilevers. And with some mentoring, we knew that we actually should prepare different structural systems for the different materials chosen. So we were working on more solutions for this cantilever, like, for example, the queen post trusses you see on the right. But we were not really happy with this solution. So we again did more brainstorming and coordination, and we decided to better have less cantilever, but have it on more sides of the building. And this then resulted in the proposed concept, Next Year Spring Sprout and Next Year Spring Steel Flower. So our architect focused to connect the past with the present and the future, with a main focus on the round earth. And the structural engineers were then again working with sustainable wooden materials like glulam, CLT, and this nanocrystal wood fiber reinforced concrete. And on the other hand, for the steel flower, we were again working with steel and more innovative solutions with 3D printed concrete. Our MEP was again working with the building orientation and also focusing on the round earth insulation. The construction managers were mainly focusing on the 3D printing process because for the sprout, we planned to 3D print the foamwork for the slabs, and for the steel flower, we were planning to directly 3D print the concrete slabs. And at the end of the winter quarter, we then evaluated these 4 concepts in a decision matrix approach. And we had a few criteria like sustainability, architecture, thrill, usability, and financing. And the winner was then next year's spring sprout. And in the following slides, I will show you on which aspects we focused on during the spring quarter and what we tried to improve for this next year's spring sprout. So one approach was to integrate, first this one. So first of all, we integrated a further approach, which was intergenerational equity. But what is intergenerational equity? So it's conserving fairness and resources for future generation. And with this, we were actually impacting all 3 pillars of sustainability. So the environmental, the social, and the economical. Also, we focused more on the 3 challenges, what our goals are, how we approach them, and how they impact the future. So for the equity challenge, we decided to work with low CO2 impact materials, and with our green roof on the roof, we added a new layer to the park. For buildings as products, we decided to develop a small kit of parts of our building elements, and we introduced key performance indicators to measure the acceptance outcome. And for parametric adaptability, we parametrized our building geometry, mainly the rammed earth walls. And by doing material iterations and including this green roof, we aimed to reach the DGNB Platinum. DGNB stands for Deutsche Gesellschaft für nachhaltiges Bauen, and its certificate measures sustainable construction on the basis of several criteria. One benefit of the public-private partnership between us, the Team River, and the Riverbank University in Weimar is the allowance for an involvement of SMEs and teaching the next generation workforce. So this involvement will be through a 10-year VR lab established by the university, and this informs the SME Sustainable Prefab Product Library. And now we start a walk into our building. So on the sides, you can see interactive information touch walls, where, for example, information about accessibility for people in wheelchairs or upcoming events is displayed. If we go up, you can see that in the middle part, we got provided with a lot of light. And also you can see these curved round earth walls, which are load bearing. There was a quick view to the auditorium, and now we go up through our glass door fire protection walls, doors to the student area. And here the more regular round earth walls are highlighting the framing. We solved many integration challenges, but I will just show you some selected ones here. So the lateral structural system is composed of the internal round earth walls and the CLT shear walls as cores. And for framing and floors, we moved away from using glulam and concrete and now use softwood and CLT panels instead, mainly for sustainability reasons. And yeah, this material choice had a positive impact on our building's global warming potential, which was measured with BOM LCA tool. I will introduce to you this later. Also, it emphasizes how we connect the past to the future. And furthermore, we decided to follow a very regular structural system, which helped us to stick to our small kit of parts. The MEP system selection was driven by the local environment, the energy efficiency, and unique properties of our building. The ground source heat pump is our primary system due to its compatibility with our site. And the round earth physical properties enabled us to use secondary systems which previously were not considered. And this allowed us to focus more on the optimization of the ventilation systems. So now we are located in the open student area in the second level, where the students get a chance for informal interaction with professors, and also they are provided big and open working areas. And the big facades open up the view to the beautiful Goethe Park. We coordinated MEP and structure system by beam underpass and beam penetration, with consideration to only penetrate in the middle 50% of the beam span and the middle 50% of the beam depth to avoid the shear and moment critical zones. Our goal was also to reach a minimum of 40% prefabricated items, including round earth walls, beams, CLT floor panels, columns, ducts, and curtain wall panels. The green roof we integrated into our building, you can see here, and also we see the continuation of the load-bearing round earth walls, which provide a shelter from the southern wind. Round earth is a central and sustainable material. It regulates the indoor humidity, it provides a good thermal mass, and it's beneficial in terms of cost and availability. And here in the ground floor, you can see this gray layer. So this is a 40 centimeters concrete layer, which provides flood protection to the round earth. Building with round earth is not so common anymore, and we had to ask the question, how do we construct these walls? So we were looking into on-site construction, but it's infeasible due to the wet climate and the flood risks. So we investigated subcontracted prefabrication and self-performed prefabrication. And using 3 KPIs, we verified that self-performed prefabrication is preferred from an environmental and an economic aspect. And this approach allowed us to focus more on the intergenerational equity again, by teaching the next generation workforce about round earth, how it's going to be constructed, and what their benefits are. And besides the prefabrication of the round earth, it was also parametrically designed. So from the initial idea, which came from our architect, we had to unify the radius such that we can reuse the formwork. And the formwork is actually the most expensive part when building with round earth. In coordination with the structure engineers, we decided to make the walls thicker, such that they are load-bearing. And to follow the vehicle constraints, we had to panelize the walls. In the end, we were also able to adapt openings to the different needs from the disciplines. The building blocks were designed with 4 different parameters in grasshoppers, and they allowed for adapting to changes in the building process. So our process goes from procurement to closeout, and our first stop is at the SMEs. So most of our suppliers were around 20 kilometers away from our site, and they were uniquely identified to take care of the kit of the items and a sustainable construction process. Then the supermarket is the home to the prefabricated packages. And it is also where the round earth walls are fabricated by the next generation workforce. But I have to add here, it's only the architectural round earth walls. The structural ones will be prefabricated by some professionals. So we then move into the quality approval and the quality control for the round earth, which is at the Bauhaus University in Weimar, and it follows the same procedure as for concrete testing. The kit of parts and the round earth blocks are delivered to site, and can be assembled with the cranes. And using this process and the prefab round earth, we are utilizing 93% of our building system from SMEs, and we initially were aiming for 70% there. And we are also at 52% prefabrication when our goal was 40%. Our process, the life cycle financial management is seldomly applied in construction to its full potential. And through the integration with our life cycle financial manager, we were able to use multiple optimized schedules through Alice, then the procurement dates from manufacturer, to find the best value for money through liquidity planning. Alice is an AI schedule optimization software, and manufacturing is a program that links the BIM model and acts as a centralized order and production tracking systems. So it helps to track the stages which the supply chain are at, and also it monitors the performance with the prefab packages. A liquidity plan was used to divide the loans over a known period of time. And when there is no liquidity plan, the interest paid is almost twice as much. So comparing the top 3 optimized sketches from Alice, we found that option 1 with 2 curtain wall crease is the winner. And we were able to save 21,000 euro that would have been paid with no value added. Our next step was to look at the risks in and out of construction. And by surveying mentors, we gained information about the impact and the probability of occurrence of accepted risks in construction. The 2 main risks were flooding and the next generation workforce. And their impact and probability were defined and multiplied together to get the severity, which could be predicted with the Monte Carlo simulation. So before I take you on the on-site assembly, here's a peek at our intelligent interoperability in design for manufacturing and assembly. In construction, we integrate Alice and Fuser to investigate scheduling and logistics. Fuser creates 4D and 5D simulations of the BIM model and helps to ensure project delivery on time and on budget. Manufacturing is used to optimize the productivity and track the supply chain. And after that, we move into a life cycle with liquidity planning and risk management, which informs supply chain and construction. And in turn, it iterates the design through visualization in Meeting VR, Iris VR, and Neuro, and modeling in Rhino, Grasshoppers, and most importantly with Revit. It combines most of the technical softwares we were using. And using all of this, we created our 5D green design for manufacturing and assembly. At first, the site had to be excavated and backfilled. Then the self-draining micropiles were installed and the concrete poured and waterproofed. Yeah. And this foundation solution helped us to avoid the risk of a shallow water table. On site, there are also 2 laydown areas where the tracks are arriving from the warehouse, and then the cranes unload the tracks and place the elements at the correct position. Our tower crane could reach the entire building footprint, and the mobile crane could only reach 2/3 of it. And this video is also showing the flood event. So the construction stops during flooding, and the site is secured by flooding barriers. A permanent earth embankment protects the building from being flooded after the construction phase. And after 227 days, the building is completed. And now let's take a quick pause on our green roof before I show you how our building performed against our goals and targets. So we tracked our building performance against the DGNB standard, and we achieved platinum certification through key design changes such as incorporating a green roof, utilizing softwood framing, implementing a liquidity plan, and green construction, which put in place pollution plans and low noise electric equipment. We also monitored the environmental and financial impacts of the proposed design changes using the sustainable target value and the target value design tools. So for example, we considered switching from 3D printed concrete slabs to CLT slabs for design and constructability reasons. And we confirmed with the STV and TVD that this change kept us within our targets. And to better understand the impact of these materials, we used this Buildings and Habitats Object Model, BOM, and its lifecycle assessment toolkit. So this enabled us to understand the embodied global warming potential of our actual materials against the evolving geometry of our building. And we analyzed 576 material combinations by parametrizing Revit geometry, utilizing the BOM to transfer it to Grasshopper, and then varying material options for the slabs, core walls, interior and exterior walls, and structural framing. And we also evaluated the impact on the TVD because a cost-effective building was our key goal. And now let's dive deeper into the TVD performance. So following the crit session on February 19th, we moved from a rough RS means estimate to the BKI Kostenplaner, and after which we consistently fulfilled our targets. So a key update was the decision to omit the 3D printed concrete slabs and commit to self-performed prefab rammed earth. We implemented a green roof and updated our general conditions based on our offsite process. This increased our cost a little bit, but with further updates, for example, the removal of the PV panels, the cost dropped down again to 7.6 million euros. And based on this framework and the framework of our PPP contract, we estimated our annual rent to the owners. So we used a rough estimate of the annual costs for maintenance and operation to set an approximate target value. And this leads then to the final life cycle costs of 18.6 million euros. To wrap up the challenges, I will point out the, to us, 3 most important approaches for each challenge. And I start with the building as a products challenge. So by using sustainable industrialization and stakeholder commitment, we were able to achieve our KPI goals with 93% SME utilization, 52% prefabrication, and 62 kilogram per square meter CO2 impact. On the parametric adaptability, we used Grasshopper to panelize our rammed earth walls. And to reach the highest DGMB certificate, we assessed the impact of our selected materials with the BOM LCH rule. Also, we created a liquidity plan to save on interest costs with the AI-created schedules. And for the equity challenge, we focused mainly on our idea to connect the past with the future in intergenerational equity. Also, we focused on the integration into the regional culture and avoid having a negative impact on the future. And with that summary, I'm very happy to mention that we won 2 of the 3 challenges. So we won the Sustainability Equity Challenge and the Parametric Adaptability Challenge. And with that, I want to show you our technology journey. So this chart visualizes which software helped us the most and were most integrated into our work. And some software were used only by a few disciplines or just by one, and others had an impact on the entire team and were really reused on a regular basis. So here I would like to mention Meeting VR. And as we never met in person, the VR software helped us to feel a little bit more connected. Another VR software is Iris VR, and this allowed us to see our building in reality and also to walk through do clash detection and clash avoidance. And the last software I want to point out is Miro, which we often used. And Miro is an online schedule, which helped us in the early stages a lot with brainstorming and problem solving. And to further give you an overview of our weekly process, I will present you a week in our life during this course. So coordination, collaboration, and cooperation were accompanying us through the entire ASC journey. And normally we started our week with updating our task in Yali Visual Planner, where we previously created a 2 to 4 weeks look ahead plan. And then we used the message platform Discord to fix our meeting dates, and also we used this as an information exchange. And when we had a meeting, we met in Meeting VR. So this allowed us to shake hands, and we also did a quick standard report. And after that, we normally moved back to Zoom to do some further discussions or decision making. And our ideas were evolving in Miro. So we developed all of our project. Afterwards, we were modeling it in Revit, and we were documenting it in OneDrive, calculating it with Excel, and in the end, walked through with Iris VR. And yeah, there were several iterations needed. So we started again in Miro, and the whole process starts again. And this leads me to the last slide. And thank you very much for your attention. And I'm very happy to answer any questions or doubts.
Thank you very much, Lisa. And it's quite impressive you're able to explain not only your parts, but the parts of also your teammates so well. So congratulations on a really clear presentation.
Thank you.
Yeah, so maybe we just start with questions from the group, and I have some later, but I'll let others start first.
You can go first. Nice work. My question is regarding, I mean, I know about the course, but I'm not really, you know, I don't really know the details of it. So if you have considered sustainability or integrating sustainability into your design, have you thought of using reused materials or products, or did you directly go to using primary raw materials?
So we mainly use primary raw materials, but for the rammed earth, which is actually from excavation material, we were focusing to really use either our excavation material, or also like from construction sites nearby to reuse this material and not have new ones. But for the wood or for the concrete slab, for example, we were focusing now on primary elements, but for sure this is an improvement which is possible if there's more time allowed. Yeah, definitely.
Nice. Yeah, and maybe one last small question. How was it with transporting rammed earth structures? How does it work? Because I only know it's to be done on site, that you ram it there. How the logistics of it?
So we rammed it in this storage facility, like the architectural walls, and there they had to stay in their formwork for 28 days that they're really dry and are fixed together. And also because of the vehicle restrictions, we really had to panelize them, that they are first of all not too big, but also not too heavy to transport and to break. And then we could transport them with a truck, and I mean the formwork is kind of still on the wall and helps to transport it and to lift it, like the piece of the wall or the panel there.
So it must take a long time because you want to reuse the formworks, right?
Yeah, exactly. Yeah.
Okay. Nice work.
Thank you.
Also from my side, congratulations. It's super interesting. So just as a reference, I think like the Martin Rauchs of this world, right? They have done this prefab rammed earth. I'm sure you've looked into this. And I think they did this for the Ricola headquarters or something. They transported the prefab rammed earth components, but I'm not. I don't know how they did the formwork stuff, and it's quite straight walls. Yet, if you want to have another reference for what rammed earth could be in the future, there's this research group in Brunswick, and they're doing this with a robot. So, not sure if this is
nice, yeah.
a viable solution as of today, but there's been research going on in this direction. So maybe this is just a pointer that could be possible. So maybe you get away with the formwork issue because you might not require it. Other than that, super interesting presentation. I like it.
Thank you. Yeah, actually, we had contact with Martin Rauch. We even had the opportunity to talk to him or to his team twice. So they were helping us really a lot because all the mentors were very critical about this rammed earth. And we really needed to have some professionals and telling their experiences and how they are working. And yeah, they contributed a lot to this project. Yeah.
Another local architect, I think, that uses rammed earth is also Professor at ETH, is Roger Bolzhauser. Do you know this person? I can also send you the link. Anyway, this is just somebody who does rammed earth in Switzerland also.
Yeah, it's very interesting. We also realized that it's coming more and more, but it's just because we also don't have any codes or any guidelines yet. It's quite critical to work with rammed earth, and you have to also trust and do a lot of quality check, what we also had to include in our project. Yeah, definitely.
It's funny that the oldest structures on Earth, I think, from rammed earth, and we don't have a code for that.
Yeah,
right?
Definitely.
That's insane.
Yeah, I wanted to ask about this, about how you solved. I'm sure that the mentors had questions about the codes, also about the structural viability, because you talk about the architecture and the structural rammed earth. So what's the kind of percentage of architecture versus structural? And how did you resolve issues around code and regulation, which I'm sure a lot of people asked you about?
Yeah, so also like the next generation workforce we had were really only building the architecture walls, which are not load bearing, and for sure they had to be on a high quality as well, but it's not load bearing. And for the percentage, I mean, now I just do a guess. it depends also because the structural walls, they were 90 centimeters thick. So quite some dimension, and the architectural ones, they were about, yeah, between 20 and 30, depends on where in the building. But I would say if we only say like the surface of the walls, it's probably 70-75% architectural walls, and the rest is structural walls. And with the codes, yeah, definitely it was a lot of discussion about that, but because we had these talks with Martin Rauch and his team, they helped us a lot with also showing already built projects where, for example, they had like 8 to 9 meter high walls, and they told us how they calculated it. And also we are incorporating a ring beam. So I didn't mention that now because it's so many different information, but between, like, after every 3 meters, we have this ring beam out of wood, which is also again transferring the loads a bit better. And this kind of helped also us to prove the structural improvements, but also because we have 90 centimeters, which is also quite conservative for round earth, it helped us. But it also, our architecture was happy with that because it makes more difference if you have also this thick walls. Yeah.
And follow-on question, because you were the structural engineer, if I remember correctly.
Yeah.
So how did you go through, what was your process like going through these kind of checks and calculations? And also, how do you feel like you were prepared as an ETH student? And then what were the areas that you had to augment and kind of come up with your own information?
Mm-hmm. So yeah, in the beginning it was, we were 2 structural engineers, so that was good that we had different backgrounds. And in the beginning, because you have this whole building, I need to know how to calculate, but you don't have time to already do FEM models for all the 4 buildings. We're really focusing on some shorthand calculations, which were quite conservative, but mainly like for the beams and the columns. And this helped us a lot to dimension them for the different materials. And I personally felt like very well prepared from ETH because we are focusing also a lot on hand calculations. So I could easily go back to all my documents and see the right formulas. And in the end, I mean, for the final project, we also had to do a finite element model for sure. And with the rammed earth, it was a bit critical because we don't have the rammed earth material itself. So we did some assumptions with thickness and compressive strength, which you put in the software. But yeah, mainly like our first approach is really the hand calculations and having these estimations. And yeah, as it is normal, what actually was a bit new for me, that it's mostly the deflection, which is the limiting aspect. So that we had to do many iterations about the span length of the beams. But it was very interesting to also talk about that, like with our architect who didn't want to have a lot of columns, but also our construction managers who didn't want to have 2 long beams. Yeah, I think there was another question, but what was it from your side?
Oh, no, you've answered it. The deflection was an issue because of the CLT specifically, versus in concrete, you usually have load, it's governing, or was it a different reason why you were surprised about the deflection governing?
Yeah, I mean, it was mainly when we were using the glulam or the softwood. For sure, for the concrete and the steel was not such a problem. But yeah, that was because of the material choice. I was astonished a bit more. Yeah, that actually we didn't need to have so thick beams or columns, but it was really mainly because of the deflection we had to increase it. Yeah.
Maybe one thing, I know we're all talking about the rammed earth because I guess it's like the like unique selling point almost of your project, but why did you decide to prefabricate it as opposed to just doing it on site?
It was mainly because of the humidity, because we are just at the river and there is this risk of flood, and also in general in Weimar the climate is quite humid, and this was just a too big a risk that the walls can't really dry enough. So in the storage area we have a control humidity and we can really let them dry, and we can, like, with this we can also improve the quality again. It was mainly, that was the main aspect. Yeah. Gotcha. And also, I mean, the ramming process, it's also an extra load. So you also need to dimension the lower stories for it if you really ram these walls on site.
And that's actually an interesting point too. Yeah. So you would actually dimension the wall differently if you had to ram 2 stories up.
Yeah, I mean, or you also, I mean, what is another option is also, but then it's also kind of prefabricate, because you just prefabricate next to the building and then put it really on its place. But then for us, it was made more sense to then directly prefabricate it in the storage because of the humidity reason. But yeah, if you ram it on the place where it has to stand in the end, it's yeah, different load, and these vibrations we need to calculate it more. And I assume, I mean, we didn't go into that because we already decided before to prefabricate them. But for example, the CLT slabs, they would never be enough for that. So I think we should have then work with concrete at least to have the ramming on place. Yeah.
So some of them are actually supported by the CLT. So you built.
Sorry, can
That's
I
why I
again?
didn't. So the big main ones, they were like load bearing, and they are ground from the ground up, right? But you're saying there are actually some architectural walls that are then supported by the wooden construction.
Yeah, exactly. I mean, the
Oh, okay.
architectural are just then in between 2 wooden columns, for example, more to separate the rooms. Yeah.
Gotcha. Cool.
Mhm.
That's probably also where you have a lot of load coming then, because I imagine there are like what's the weight to like typical concrete wall? Are they like heavier, 2 times heavier? What's the kind of difference between the rammed earth and the concrete walls?
Yeah, it's actually compared to concrete. I mean, concrete is 25 per cubic meter, and rammed earth is 21. So it's not. It's actually lighter, but because, I mean, especially for the structural ones, if you have like 90 centimeters, or if you have like a concrete of 20, yeah, that's the load then. But as I said, like the architectural ones had normal thicknesses, also because of the space. So we didn't want to take away too much space. Yeah.
I have a small question. Do you consider operational energy in the building? I didn't hear talking a lot about it.
Yeah, I mean, we touched it a little bit, but not in very detail. Yeah.
Okay.
Yeah.
Oh, so do you guys did the project life cycle, the building life cycle assessment? For example,
Yeah,
like, yeah.
Mm-hmm.
Sorry, yeah, please go ahead.
Yeah, with this BOM tool, it helped us a lot to have this life cycle assessment, and also include all the materials and how they, yeah, like the different materials, how they behave and how they perform. Exactly. But I have to also say that was mainly the MEP engineer, so she also did a lot of research there, but we always, like, we informed each other, but not about everything. So, but I can for sure ask her again and reach back to you if you're interested.
I mean, it's like a maintenance for the materials, and also how about the end of life of the building?
Yeah, I mean, we considered in the life cycle costs that we have to, yeah, consider this maintenance, and also the, yeah, in the end, how the building is maybe reassembled, whatever. But it was mainly an estimate for the costs and not the process. So we didn't go through and had an approach how we really gonna maintenance, what are the steps, what we need to do, because it was just, yeah, the time was a lot of limiting aspect. But our lifecycle financial manager considered it in the costs with some estimates from former buildings. Yeah.
I wanted to ask about your kit of parts approach with this was done for both. I think it makes sense. I understand from the panels standpoint, from the rammed earth standpoint, how you had these 3 different designs, and it was parametricized with Grasshopper. And then for the CLT, how did you define the kit? Were you doing like same column size and similar beam sizes? Were you varying the beams from the edge to interior beams, or were you using the same? And how did you decide the trade-offs in standardization versus cost on a project basis?
Mm-hmm. So we were focusing really on the rammed earth for the kit of parts, but also the beam. Since we had this regular structure system, it was actually quite easy to have at least the same cross section. But sometimes, because we also have these cantilevers, we also had to have specific sizes. So therefore, we realized it doesn't work now for us to focus also to have a kit of parts for the beams. So we were focusing on the columns, and for the columns, we really have, because of the different room heights. This was also limiting, but we have 5 different columns, and this helped us a lot also in with the cost because they're also prefabricated. So then we just had a bunch of same type of columns with length and cross section. And the CLT panels, we focused here on the CLT floor panels to also panelize them. For the cores, just in the end, we didn't have time to also work with that, with the openings of the doors, etc. This can be for sure improved. But the floor panels, we also, because of the structural, the regular structure system, it was easy for us to have it in different panels. And also, I think it was in the end also 5 different panels, different sizes, yeah.
And you mentioned you had, I saw in your workflow, you had Alice and you had Manufacton. Well, you had an arrow between them, but can you speak to how were they integrated, or were you passing information from Alice and Manufacton? I'm just curious how you set up the interoperability between the two.
Mm-hmm. So we started in Alice and did the different schedules from it, and then we took out like the best schedules, or like several best schedules, and with the Manufacton we can, I mean, put in this schedule and all these milestones, and then Manufacton gives us the simulation of the production tracking and everything. Yeah. So it was always starting in Alice, and then we went to Manufacton, and then we also went to Fuser. And if we saw problems in Manufacton or Fuser, we had to go back to Alice and did some iterations. Yeah.
And how did you find Manufacton? I've had mixed feelings about the software. I think it's growing a bit. What was your team's conclusion on that?
I personally was not working with Manufacton. It was mainly our construction managers, but they were also sometimes complaining about it, and that it was not so clear, like not understandable, but just a bit contradictory sometimes. So yeah, we also as a team said, okay, let's focus really more on optimization and have a good schedule, and then do this iteration, not like too many times that you're not losing your nerves. Yeah. But I think the visualization is quite nice, and also that you see the different stages, and also it's coloring the BIM model where we are at the moment. But yeah, I think there's a bit improvement possible as well with Manufacton. Yeah.
I have a last question if there's no more. Anybody else want to go? Yeah, so this is, I've asked all the students that have done the course, what were this is, you know, I asked you already about as a structural engineer, but then more generally about teamwork, about collaboration, about kind of realizing a real project, or as close to a real project as you can get in a university setting. What were your biggest things that you learned, or skills that you gained in the process?
Mm-hmm. So what we also did like wrong in the beginning, it's really communication and collaboration is key. Without it doesn't work, and especially interdisciplinary, not only between the two structures, but also in the whole team. Because any change you are doing or any new idea you're thinking of and you're not communicating, it causes problems in other disciplines. And that was really a key point I learned. And I mean, as we discussed also before the presentation, that I did a project work about IPD, and I really saw, because with this public-private partnership, it's also this direction of IPD. So I really saw that it's so important to have everybody on board from the beginning, because there are so many restrictions also from the construction managers, which are limiting design, or which are also giving opportunities for sure. So that's really key. And yeah, after we did some mistakes, we really realized it's very important to sit together and to meet, especially architect and structurals in the beginning phases, and I really always communicate. But also in terms of the real project, I mean, it's hypothetical, but still it's very real, and it's very interesting to see what else besides like my part I know from structural and also my construction management background, what else is in a building, especially MEP, which we never learned about it. I mean, a little bit, it depends on what course you're taking at ETH, but it was so interesting. And also we had a lot of problems with the room height, and because of the shallow water table, everything was working together. And it's, but why do we need this duct? Why do we need to be 30 centimeters, and to find like solutions for this, that was really interesting. Yeah, again, like this interdisciplinary way, and yeah, also really having a kind of a real project. It's very cool to see. I mean, I don't know, but I assume that it will be similar like this in the work life, but maybe it's also different because we don't have IBD projects yet. So yeah, it was a really nice experience to have like your knowledge and to put your experience in it and see and also learn from other disciplines. And as you said, Professor Hall, in the beginning, that I also know how to present other disciplines. That was also really our main goal. So for the winter presentation, we didn't want to say like, okay, structures are presenting structural, CMs presenting CMs. So we really switched all the disciplines. So nobody was presenting their own things, which was quite challenging, I have to say, but I learned so much also about other disciplines, and it was really interesting. So also for the whole spring quarter, we always did that when we had presentations, and you really know what's going on and what are the opportunities. And that helped me a lot to widen my horizon. Yeah, definitely.
Great. And I didn't mean to laugh too much when you say, I think it'll be like this in the future, but my experience is in 90% of the cases, unfortunately, it will not be like that.
Okay.
We hope things are changing, but I think both from a technology side and from a collaboration side, that existing practice is nowhere near what you just did. So not to make it feel like, oh no, but that's just the reality is the industry, especially if you're going to work in Switzerland. My impression is not at this level of collaboration or coordination. So, but you can change it. You could be one of the people that brings the change. So, and there are also lots of good people working in the change. So I don't mean to be too negative about it. Just made me laugh a little bit. So.
Yeah, definitely. I think there is a lot of improvement possible. That's true. Yeah. Okay,
so I think that's all for Lisa. Thank you so much. I mean, it's really cool to see, yeah, how far you got. I mean, that was a really impressive project, and 2 awards. That's great, and I think really also showing the skills that ETH brings, demonstrating to the international community is also great that you could do that. So thanks for all the efforts and time, and really nice work.
Thank you very much, and thank you for the opportunity to present that. It was a pleasure. And also thank you for all the questions and feedback.